All right, so in part one, we saw where that derivation came from. Again, definitely a good one to look over as we go through, an important one for you to make sure we feel comfortable with. Example one here. And to be honest, example one is going to be enough work. I'm probably going to pull up a blank page. This will probably take most of this video, and that's okay. But it's a question we definitely want to make sure we can break down. So I'm going to go ahead and actually do that. I'm going to pull up a blank page for us to work this one out here in just a minute. I might write down the key features first. But anyway, they break it down, and this is just going to be more practice for us with what we've seen in the last couple sections. So at time of 0, we've got a 500 gram, so a 0.5 kilogram block, so a 0.5 kilogram block, oscillating on a spring that is moving to the right at x equals, I'm going to go ahead and convert that to 0.15 meters as well. It reaches a maximum displacement of 0.25. So if that's the maximum displacement, think about what that tells us. That would be the amplitude, right? And it tells us that that happens at a time of 0.30 seconds. The first part wants us to draw a position versus time graph for one cycle of its motion. So show at least one full cycle of this object as it's oscillating back and forth. And then part B, at what times during the first cycle does the mass pass through x equals 20 centimeters? So the tricky thing about this question is the fact that they don't give us the period. They don't give us the period or the frequency, right? And so we don't immediately know those, because if you knew the period and the frequency, you could kind of break this up a little bit, just piece by piece, and kind of at least get a general feel for what your graph would look like, right? We know that it's not starting at the amplitude, but over here at like 0.3 seconds, we know that it's reaching an amplitude. And if you knew the period, you just kind of break that up into quarters, and you could work from there. Again, the problem is we don't know the period right now. So like I said, I'm going to go ahead and pull this up as a fresh page. But what we want to do on a question like this, we definitely want to make sure that we are, as we set this up here, that we are taking our time and writing our position function for this, right? In order to be able to do this, we're going to have to find our position function in order to first kind of figure out then what's going on, right? And so that's what we're going to do first, is we're going to set up our position function. Okay, so I'm going to do x equals a times cosine of, and I don't know either the frequency or the period, so it doesn't matter a whole lot which one you start with. I'm typically going to start with the period, because when I'm making my graph, the period is going to be the one that's more helpful for me to include. The other thing I do have to be very mindful of on this one is I definitely need a phase constant, right? And I know that I need a phase constant because it's not starting at the amplitude. Or if you go back and reread the question, it tells us it's starting at x equals 0.15 meters, right? That's where it's starting at a time of 0. And it tells us later that the amplitude is in fact 0.25 meters from the equilibrium position. So that's something we need to keep in mind as we build this function. But let's go ahead and start to plug in what we do know for the function. And so I'm going to take advantage of the initial conditions. So remember, a lot of times when we're finding the phase constant, it's almost like how we find our plus c when we do our integration, is we take advantage of the fact that we know at a time of 0, x is 0.15, right? So that's a helpful piece of the puzzle. So I'm going to go ahead and plug in 0.15 for x. I'm going to plug in 0.25 for a. And then again, it's cosine of, but because I know the initial time is 0, the best part about that is I don't even need to know what the period is right now, because that whole part there is just going to become a 0, right? This entire chunk here is just going to go to 0, and then plus the initial phase constant. So this actually gives me a route to pretty quickly, hopefully, be able to find the phase constant. So I'm going to divide both sides by 0.25, right? And then see what I get from there. I'm going to go ahead and leave this as a fraction, but you could do it obviously as a decimal too. 0.15 over 0.25 is 3 over 5 3/5, or 0.6, right? And then cosine of our phase constant. So if we're trying to solve for our phase constant, again, hopefully most of us feel pretty comfortable with this. We are going to do cosine inverse of both sides. So I do cosine inverse of the right-hand side, it cancels it out. And then I do cosine inverse of 3/5. Now, a lot of these, like as we see in this question, they're not necessarily going to jump out to you as, oh, I know where 3/5 is on the unit circle. And so here's where we're going to have to do a little bit of thinking as we go through this. So I do want us to, let's think about the unit circle over here first. So if we're thinking about positive 3/5, and since we're looking at cosine, again, we're thinking about the x value. So where would the x value be 3/5 on the unit circle? Well, we know all the way over here at the amplitude, the x value is 1, right? So 3/5 is going to happen somewhere between the y-axis at 0 and 1. So if I'm just kind of estimating, maybe here's about 3/5. So then x would be at 3/5 either here or here on my unit circle, right? Now, what I have to keep in mind is I can definitely use my calculator as long as I am in radian mode, so make sure we're in radian mode as we do this. But I can use the calculator to check and see what cosine inverse of 3/5 is. The thing that we have to keep in mind is the answer that gives us will be the answer that falls within, right, the first half here of the unit circle for cosine. So it'll check somewhere between 0 and pi. But let's go ahead and do that first. So let's find that cosine value. Cosine inverse of 3/5. If we type that into our calculator and we are in radian mode, then that gives me about 0.93, right? And so what that shows me, and that makes sense because it's an angle that's measured between 0 and pi, and we knew that it should be somewhere between 0 and pi. So that tells me that this position up here would be when theta is 0.93 radians, right? So this is one of my possibilities. The other possibility, though, is, again, it could be down here because that would have the same x coordinate, right, as the other one. And so here's where we have to go back to the question and make sure that we're thinking about this, because the question actually does tell us more than what we were originally expecting, maybe. So if I go back to the actual question and I look at that, it says at the time that it was moving at 15 centimeters there, it's moving to the right, meaning it's going towards the positive amplitude. So if I'm looking at these 2 points, this point down here is the one where it's still moving to the right. It's still moving towards my positive amplitude. So I have to be careful because even though the calculator spit out this as my answer, that is not the radian value that we want, right? That's just the positive value up there, but we want the value that would be down here. Now you actually have a couple choices when you're finding this value down here. You could find this as simply negative 0.93 because that's how far it would be, right, from that negative axis. You can do that. I actually am going to choose, though, to, instead of finding a negative value for my phase constant, again, mathematically it doesn't make any difference because they'll represent the same thing, but I'm actually going to choose to do 2 pi minus 0.93. And that's just to keep the phase value or the phase constant as a positive number. Again, it won't make any huge difference for us mathematically as you calculate this. But I'm going to choose to do 2 pi minus that value because if I went all the way around the circle, that would be 2 pi radians, but I went 0.93 radians short of going all the way around the circle. So 2 pi minus 0.93, which if I round that off, is about 5.36. This is the phase constant. This is the angle that represents my starting position here, right? If I started at the x-axis and I went all the way around there, that's my initial phase constant, and that's the value that I'm going to use. So a lot of work to set that up. Again, I know it's tricky. I hope that as we do this more, we're getting more comfortable. But I now know the phase constant is 5.36. And then this allows me to fill in a little bit more for my equation, right? So if I come back to my equation, x equals a times cosine of, I'm going to again use 2 pi little t over the period, and then plus the phase constant. And then I'm going to plug in what I know now. So I'm going to leave this as x for right now. 0.25 cosine of 2 pi t over the period, which I still don't know the period, but I do know plus 5.36 is my phase constant. So believe it or not, that does actually play a big role for us. It helps us fill in the puzzle. We still have a little ways to go though, right? So the next thing that I'm going to take advantage of is the fact that they tell me in the question. So again, if you go back to the question, it tells me when the object first reaches the positive amplitude. They tell us we first reach the positive amplitude of 0.25 at a time of 0.3 seconds. And that's helpful because that's going to help me finish out and find the period for this function. So I'm going to plug in 0.25 for x because that's the position that I'm at. And then for the time, I'm going to plug in 0.3 seconds and then try to solve for my period. Once again, doing this, I've got to be careful. So dividing the 0.25 over is obviously just going to be 1. And then I have cosine of this whole mess, right? And then from here, I still do the cosine inverse of both sides. That'll cancel out the cosine on the right-hand side. And again, here's where I need to be careful. So where does cosine, right, where is our x value on the unit circle equal to 1? Well, I think hopefully most of us are pretty comfortable with that. Cosine is equal to 1 right here, so that's at either 0 or 2 pi, right, or any multiple of pi. Now, because I chose my phase constant to be 5.36, I actually do not want to choose 0, because 0 would be as if it were starting here, but it had somehow gone back in time and started at 0. So if you had chosen the negative 0.93, you absolutely could choose 0 because that would be beyond that point. But since I chose 5.36, I need to make sure that I choose 2 pi, because 2 pi would be the first time after 5.36 that I actually end up at that location where cosine is 1. So I need to make sure, for me, I'm going to do 2 pi. Again, if you had chosen to use negative 0.93, that's perfectly fine. You would choose 0 because that would be the first time after this that happens. From here, though, not too bad to solve this the rest of the way out, just a little bit of algebra, and we can solve for our period. So sure enough, if I subtract 5.36 over, I get 0.93. This is where, at this point, yours should look exactly the same, because if you had chosen negative 0.93 and 0, you would also have 0.93. So that proves that we're on the same page. And then to solve the rest of the way for the period, I simply multiply by the period, divide by 0.93. And when I do that, I get the period to be about 2.03 seconds. I'm going to go ahead and approximate that as about 2 seconds. I know 2.03 is a little bit more accurate, but I'm going to use that as 2 seconds because it's going to help me graph this a little bit more easily. So anyway, let's get to that, because at this point we've found what we need to find to build our function. I know it's a lot of steps. I know obviously it's been 12 minutes of this already. So it does take a little while to do this. Now you'll get quicker the more you practice this. But it definitely takes a few minutes to get here, right? But the good news is we have the function now. And since they asked us to graph this function for the full cycle, you can now just, like if you have a calculator available, hey, you can just plug this into your calculator and then kind of take it point by point and then trace it out enough to where you can actually plot it. Now I want to show you though how you can do this without a calculator too, because we know we very well may need to do that. So if that ever happens without a calculator, this is how we can take it from there. So here's my advice on how to make this graph relatively simple. So I'm going to start at obviously the first location I knew, which was at a time of 0. They told me I was at 0.15, positive 0.15, right? And I was approaching the positive amplitude. So I'm going to go up by maybe 0.05. So each of those is going to be 0.05, which tells me then at a time of 0, I'm starting up here, right? The other thing I know that's very helpful is they tell me at a time of 0.3 seconds, I am now at a position of 0.25, because they told me that's when I reached the first positive amplitude. So I'm going to go up by maybe tick marks of 0.1, so 0.1, 0.2, 0.3, and then I know that at 0.3 seconds, I'm now up here at 0.25 on my y-axis. Now that becomes a critical point for me. That becomes a point that makes graphing this way easier, because if I know one amplitude and if I know the period, I know that the period can be broken up into quarters to show us kind of the remaining critical points. So the reason that I rounded this off at 2 is because it's really easy to break 2 up into quarters, right? If I divide 2 by 4, it gives me 0.5. So every 0.5 seconds, I should progress from one amplitude to equilibrium or to the next amplitude and so on. So in other words, if this was at 0.3 seconds, I know over here at 0.8, obviously that's not scaled very well, but 0.4, 0.5, 0.6, 0.7, 0.8, that's when I should be in equilibrium for the first time. Then I know over here, so again, that's at 0.8 seconds. At 1.3 seconds, which I'm just adding another 0.5 on top, that's when I should be at the negative amplitude, right? And so on and so forth. So I can pretty quickly build the rest of my picture here, right, by simply counting out every 0.5 seconds. And that gives me a way to pretty quickly graph this while still getting specific points, but not having to stress about doing like at random locations. And that definitely shows me at least one full cycle. So a lot going on with this one. take your time on the graph. I'm going to finish this up in the next part of the video, and then we'll stop there.